Hi guys, Daniel here, and last video we did a problem from an anime called Madoka Magica. This video I'll solve a sort of generalization to that problem, a problem with greater difficulty. I decided to split this into two videos because the difference between the difficulty of this new problem and the previous problem was a little bit too big for them to be put into one video. So I hope you enjoy this generalization. Anyways, it goes like this. Same thing, we have a p be a prime and n be any positive integer. 1 plus n power of p minus n power of p minus 1 we want to prove is now divisible by p squared instead of p. But of course we're given an extra condition, or else this problem would be very false, which is that p divides n squared plus n plus 1. This is a condition that you know is true. So we have to prove this divisibility by p squared given this condition and the fact that p is a prime. So how might we go about doing this? Well, first off, we might want to see what we could do in the previous video that we might still be able to do in this video. Well, if we do a binomial theorem, it seems like it would be bound to fail because we're taking mod p squared, not mod p, and any of the binomial coefficients aren't divisible by p squared. So it'll be a very big pain to solve it like that. What about Fermat's little theorem? Well, the fact that we're taking mod p squared instead of mod p already sort of doesn't really make that work anymore. It won't be as nice as before, so that's pretty much out of the window as well. So back to the drawing board. We have this extra condition, p divides n squared plus n plus 1. So we might as well want to try to come up with what p can possibly be. In order to do this, we'll need to use something called Legendre's symbol. So Legendre's symbol is a compact way to represent if a number is a quadratic residue mod p. Well, a quadratic residue is basically this. So let's say that a is a quadratic residue mod p. So we're taking mod p, and we say a is a quadratic residue mod p if there exists an x such that x squared is congruent to a mod p. This kind of makes sense with the name because a quadratic residue would be a residue of something that's quadratic, and x squared is certainly quadratic. So in order to represent this in Legendre's symbol notation, we write this: a over p with parentheses surrounding it equals 1. This tells us that a is a quadratic residue mod p. If this equals -1, then it tells us that a is not a quadratic residue mod p. So that means there does not exist an x such that x squared is congruent to a mod p. And finally, when this is equal to 0, then it means that a is a multiple of p. So now we know what the Legendre symbol says. We should also go through some of the properties in order to solve this problem. First off, the Legendre symbol is completely multiplicative. This means that for any numbers a and b, a over p times b over p is equal to a times b over p. So this is a completely multiplicative function. In addition, there's a very useful theorem dealing with quadratic residues called the quadratic reciprocity theorem, which states the following: if p and q are odd primes, they have to be odd, they cannot be 2. This is very important, so you don't make that mistake. If they're odd primes, p and q, then p over q times q over p is simply equal to -1 to the power of p minus 1 over 2 times q minus 1 over 2. We will also need this theorem in order to solve this problem. So with these two theorems in mind, let's try to find what possible p's satisfy p divides n squared plus n plus 1. So first off, we know that p is not 2 because n squared plus n is a multiple of 2, so therefore n squared plus n plus 1 is odd. So we can safely say that p is greater than or equal to 3. Now we can multiply the right hand side by 4 safely because p is not 2, and the divisibility will still hold true. In other words, if we factor the right hand side, we get p divides 2n squared plus 1, 2n plus 1 squared plus 3. So in other words, 2n plus 1 squared is congruent to negative 3 mod p. So now we see where quadratic residues and Legendre symbol fits in. We have a number squared is congruent to negative 3 mod p, which implies that negative 3 over p equals 1. In other words, negative 3 is a quadratic residue mod p. So what does this simplify to? Well, we can use this property of the Legendre symbol, completely multiplicity, in order to turn this into negative 1 over p times 3 over p. Alright, one more property that we cannot forget about Legendre symbol is the following. A over p is congruent to negative 1 to the power of a, or sorry, not negative 1, a to the power of p minus 1 over 2 mod p. So a over p is congruent to a to the p minus 1 over 2 mod p. Notice that if we take a to the p minus 1 not over 2, then by Fermat's little theorem, this is congruent to 1 mod p for a not divisible by p. So when we take over 2, this thing can be congruent to 1 or negative 1 when a is not divisible by p, and 0 when a divides p. So this meshes with our definition that a over p is equal to 1, negative 1, or 0. So this is an alternate representation of the Legendre symbol, and in this case we'll use it here for negative 1 over p. A corollary of this is, of course, when a equals negative 1, that negative 1 over p is congruent to negative 1 to the power of p minus 1 over 2 mod p. But in particular, since negative 1 to the power of p minus 1 over 2 is going to be either 1 or negative 1, negative 1 over p is in fact equal to negative 1 to the power of p minus 1 over 2. P minus 1 over 2. So we can set this thing as equal to negative 1 to the power of p minus 1 over 2 times 3 over p. So now how do we deal with this 3 over p? Well, now we can use the quadratic reciprocity theorem to turn this into something a little bit nicer to deal with. In particular, 3 over p is equal to, let's put that negative 1, p minus 1 over 2 here, is equal to negative 1 to the power of p minus 1 over 2 times q minus 1 over 2, where q is equal to 3. So basically 3 minus 1 over 2 is just 1. So this just turns into negative 1 to the power of p minus 1 over 2, divided by q over p. So the fact that we know that q over p is either 1 or negative 1 tells us that 1 over q over p is just equal to q over p. So this is just times q over p, where q is, or p over q. So p over 3. Again, we already have a negative 1 to the power of p minus 1 over 2 on here, so we put that right here. Then we plug in q equals 3 into the quadratic reciprocity theorem to get 3 over p is equal to negative 1 to the power of p minus 1 over 2 times q minus 1 over 2, which is just equal to 1. So just p minus 1 over 2, which is this term, divided by p over 3, except for the fact that 1 divided by p over 3 is equal to p over 3, since p over 3 is either 1 or negative 1. So that means we can just say multiplied by p over 3 instead of divided by p over 3. Anyways, these two terms cancel each other out pretty nicely to get this is only equal to p over 3. So now our question is, for which primes p is p a quadratic residue mod 3. And of course, we already know that all squares are congruent to 0 or 1 mod 3. So that means our only possible values of p are p is congruent to 0 or 1 mod 3. So in particular, if p is equal to 3, then it's 0 mod 3. Otherwise, we have p is congruent to 1 mod 3. So now we know what certain values p can attain. We have to go back and prove the original statement. Of course, since we already seem to naturally have two cases here, p equals 3 and p congruent to 1 mod 3, let's consider the problem in these two cases separately. If p equals 3, so let me write the statement over again. 1 plus n power p minus n power p minus 1 is divisible by p squared. So we want to prove p squared divides n plus 1 to the power of p minus n to the power of p minus 1. So if p is equal to 3, then that means that wait a second. When p equals 3, the problem is false. So let's just pretend that in the beginning we said p is not equal to 3. Yeah, okay. Sure. Alright, let's just assume that p is not equal to 3. Since when it equals 3, it's obviously false. Just take n equals 2, or 1, for example. Because then we get like 8 minus 1 equals 6, which is clearly not divisible by 9. So let's assume p is 1 mod 3. Alright, so let's see what happens when p is 1 mod 3. Well, in order to prove p squared divides m plus 1 to the power of p minus n power of p minus 1, well, we already know that p divides n plus 1 to the power of p minus n power of p minus 1 because all of the coefficients of n are divisible by p by our previous video from Madoka Magica. So in order to prove p squared divides n plus 1 over to the power of p minus n power of p minus 1, we think about polynomial divisibility. In particular, if we prove that n squared plus n plus 1 divides n plus 1 to the power of p minus n to the power of p minus 1, then we will be done. Because if we prove this polynomial divisibility, then since n squared plus n plus 1 is a monic polynomial, i.e. a polynomial with leading coefficient 1, then if it divides this thing, then it divides this thing over p, since p is just a random constant. In other words, because p divides n squared plus n plus 1, then that means n plus 1 to the power of p minus n power of p minus 1 over p is divisible by p, so this expression is divisible by p squared, and we would be done. So we just need to prove this polynomial divisibility. N squared plus n plus 1 divides n plus 1 to the power of p minus n to the power of p minus 1. How might we go about doing this? Well, by the factor theorem, we know that if we prove that all of the roots of this, when plugged into this thing, make it vanish, then that means that this thing is divisible, or divides this thing. So what are the roots of n squared plus n plus 1? Well, the roots are just the primitive third roots of unity. In other words, e to the 2i pi over 3 and e to the 4i pi over 3. Since these are just complex conjugates of each other, I'll just check one of them. The other one's identical. So let's try plugging in n equals e to the 2i pi over 3 in for this thing and hope it becomes 0. So e to the 2i pi over 3 plus 1 to the power of p minus e to the 2i pi over 3 times p minus 1. First things first, since we already know that p is congruent to 1 mod 3, then let's see if we graphed e to the 2i pi over 3 onto the complex real plane. It's this thing right here. So if we multiply by p over here, it's basically going around in this many degrees p times, and since this is 120 degrees, going around p times is going around 3 times plus an extra time. Since 120 times 3 is 360, it's basically just going around a full circle and then going one more, which is just this point again. So this thing is just equal to t to the 2I pi over 3. Over 3. There. Okay. So now we have also a minus 1 here. And now we need to find this thing. So what is this thing on the real complex plane? Well, if we add 1, then we reach this point. This is a terrible diagram, but this is supposed to be an equilateral triangle, which means that this point is one of those primitive 6 roots of unity. In other words, this is 60 degrees. And now we want to take this complex number to the power of p. So now p congruent to 1 mod 3 doesn't tell us enough, because then we can either have that it is equal to like this point or this point, which unfortunately is not enough to solve the problem. However, we also know that for all primes p greater than 3, that p is congruent to 1 or 5 mod 6. And this is actually quite an easy statement to prove, because we know that p is not congruent to 0 mod 2, and we also know that p is not congruent to 0 mod 3, so by Chinese remainder theorem, only these two values remain. So since p is 1 mod 3, and p is either 1 or 5 mod 6, we know that p is 1 mod 6. In particular, this means that we're going to go around the circle, complete circle, and then plus 1 extra, because this is 60 degrees, and going around 6 times goes back to normal. So once we go around 6 times a integer plus an extra 1 time, we're back to this position. So this thing is just equal to e to the 2I pi over 3 plus 1, or plus 1, and we subtract this. But this entire thing is just equal to 0, so indeed, when we plug in n equals e to the 2I pi over 3, the right-hand side vanishes, 0. So that means, again, we can do the exact same thing with e to the 4I pi over 3. It's the exact same calculation. You can check it yourself. But anyways, we find that n squared plus n plus 1 divides n plus 1 power p minus n power p minus 1, which means it divides that thing over p. But since p divides n squared plus n plus 1, we know that p squared divides n plus 1 to the power of p minus n power of p minus 1, and we are done. In fact, a stronger result holds is that p cubed divides n plus 1 power of p minus n power of p minus 1. This problem is left as an exercise to the watcher. Hi guys, it's Daniel here, and last week Zon did a math problem from Assassination Classroom. So this week I was watching Madoka Magica,